So, welcome to the class. This is high performance computing and applications. Okay. So, this course number is IDC 606A. Okay. So, this course is deals with HPC. So, supercomputing, it used to be called earlier supercomputing, but now it is called HPC. The reason why it is called HPC is it's not only computing, it deals with the data structures, storage. Also you will find that there are a lot of communication between processors. Okay. So, we will deal with lots of these aspects. So, that is why it is called HPC. Now, question is, why do we want to worry about computing? Okay. So, there are some students, I am sure, well, I think all of you are interested in computing, but there are some people who think computing is not necessary, right. We can think all of it in the head, no. So, it turns out not a lot of things can be, you can imagine things, you can solve mathematical problems, but there are problems which cannot be solved by just theorems or pure mathematics. Okay. So, which are the problems? So, let us look at some problems. Most of the problems we deal with today is very complex, they are like weather, I mean, okay, that is or air conditioner. To design a very efficient air conditioner, it is complex problem, it is not simply some equation you solve it and you will get the answer. So, analytical tools do not work, you cannot write down mathematical formulas for lot of problems. So, actually in fact it turns out the solved problems exactly solved means you have a answer in terms of sine, cosine and so on, so it is exactly solved, like Kepler problem is solved, no, you have a solution, the planets follow an orbit or follow elliptical orbits, we know how to solve it. In fact, Newton did that first. But as soon as you put another body, like 3 body problem, so instead of planet and the sun, we have moon, okay. So, moon, planet, moon, earth and sun, it turns out there is no exact solution. We cannot write down things, we cannot write exact solution, the trajectories are not elliptical orbits anymore, in fact they are chaotic for some parameters. Okay. So, in fact it is very hard to figure out for which parameters things are chaotic. Okay. So, the problems which are we know how to solve, it turns out 2 of them is hydrogen atom, or that is connected with Kepler problem in classical mechanics and oscillator, right. It turns out both these problems are solved analytically, both in quantum and classical. But as soon as you put third particle, in fact helium atom is not solved, okay, there is no exact solution for helium atom, hydrogen atom has an exact solution. So, then what do you do? So, you have done in your quantum course, right, that you solve by perturbation. So, we put in new another particle, we apply perturbation theory, or we go to computers. So, you solve using numerical method. It turns out it is much more efficient nowadays to put in a computer rather than writing these long formulas for perturbation series, and perturbation series typically is good for small parameters, but in computer you can solve them for any parameter. Okay. It is typically not exact, but numerical solutions can also give you exact solutions. Are you aware of some solutions which are exact? So, computer does not mean it is always approximate. Okay. Can someone think about some exact solutions? Computation can give exact solutions. So, Gauss quadrature can give exact solution. So, for if your function it is of polynomial n, then you need n by 2 number of roots and the weight function. Okay. So, in fact it is exact, you can get a number which is as good as what you do in Mathematica. Okay. So, numerical methods are important for many applications. So, you should also keep in mind that computer simulation is like numerical experiment. Okay. Now, it is very powerful analogy. Why is it powerful analogy? Why do you do experiments? because we may have a theory and we want to verify the theory, right. In physics you may know that no theory can be proven like mathematics. Why? Because there are assumptions, we always make assumptions and those assumptions may not hold in nature. So, basically nature is a test, we are trying to make model for some phenomena in nature and that phenomena may be more complex than what we modeled with. Okay. For example, Newton assumed that time and space to be absolute, which is not true, and Einstein figured out that it is not true. So, but Newton was right in his time and it gave a very good predictions for planetary orbits. So, the basic paradigm in science is that you make predictions and you then verify it with experiments, and if it works then you say, well, good, my model is working well so far. But any day some experiment comes and says, well, it is not matching, then something has to be done with the theory. Okay. So, that is how experiments are very important, and experiments also give you ideas for new theories. Okay. Einstein theory comes from which experiment? Michelson model experiment. No, I meant relativity. Okay, quantum theory of course came from, well, major contribution is photoelectric effect, but relativity comes from Michelson model experiment. So, experiments also lead to new discovery, new theory. Okay. So, nowadays instead of doing physical experiments, we can do computer experiments. Okay. Now, you may be surprised what is this computer experiments. So, presently for aeroplanes, okay, making new aeroplanes, you don't, I mean there will be many designs, right, I mean there will be 10 designs. Some very clever engineers make design and then they say, well, let us try this out. But making 10 aeroplanes, even a model like small aeroplanes are expensive. Okay. But what do you do? Well, typically what they do is they put it in a computer. So, there are surfaces can be made in computer and then we apply Navier-Stokes equation and we can look at the flow profile and see the drag, efficiency and so on computer, and then out of 10 you can choose 2. You can discard 8 saying, well, these 8 are not very good by computer simulation itself, but then with those 2 of them we need to do experiments. Computer simulation is not fully reliable and we need to validate the computer model with simulations, with experiments. Okay. So, all these rockets which are sent up, so there are simulations done before and they are validated at least for some parameters. It turns out some parameters you can't do, some parameters cannot be validated in the lab, then what do? You say, well, let us shoot the rocket and we will see. So, that is also a problem, but some experiments can be done in the lab. Like a lot of NASA missions, they have you might know, you have seen some films, no? They have a room with almost zero gravity. Okay. No, real experiments. They rotate in such a way that gravity is cancelled out, and so there are places where you have to put in human being, right? I mean, these astronauts are going up, we can't simply. So, there are simulators. So, the rockets are tested in real life situation, sorry, not real life situation, then they are sent up. So, what I am saying is experiments and numerical simulations go hand in hand, and now there are optimum ways to do it fast. So, there is one person whom I met. So, metallurgist, he said earlier to make a new material for aircraft, it used to take something like 5 to 10 years. You have to do experiments, no? I mean, then so this material, how hard it is, how means it should be light as well as what I mean, should not have cracks, should be very robust. But with computer simulation, that time has been reduced to 1 or 2 years, because we can search for that kind of material in computers and then we do less experiments. Okay. So, this is a very important aspect which is giving lot of benefits, like corona virus. the vaccines, the simulations played a big role. We wanted vaccines soon, right? So, typical vaccines take around 5 years or longer, but this vaccine came in 1 year. So, these are the experiments and we make model based on numerical results, often complements experiments. There is one more point which I do want to make, I mean these are some general statements I am making. Sometimes it is very hard to probe certain things in experiments. Okay. In astrophysics we can't do experiments, right, typically. There are observations, but we can't do experiments, but here computer experiments are very valuable. Like galaxy we can simulate in our computers, and but we can't have galaxies in our lab. Secondly, there are fluids, we can't see through the fluid. Water we can see through, but there are metals, liquid metals, the terminator, right, I mean that is a liquid metal, we cannot see through the liquid metals. So, what is the property inside the fluid? We can better to simulate. Okay. So, these are complements, excellent visualization. Okay. So, in experiments, typically in fluid experiments we put a probe. So, in this room I want to measure the flow profile. So, I can't really take a picture of the full 3D air in the room. No? In fact, air is we do not even know, we can't see it visually. You can put some tracer particles. So, you can, how many tracer particles can you put? Maybe 50, 100, and you can track them. Nowadays there are very good ways to track them electronically, visually and so on, but they are limited number of probes you can put. Okay, you can put thermometer in some n places, but in simulations I can put billions of probes, right. I mean I can put lots of places where I can measure velocity. In fact, we solve for those velocities. So, I have very detailed picture of the velocity field. So, visualization is very good. Nowadays we have 3D visualization, not nowadays, I mean it is quite old. With virtual reality we can we have those glasses and you can see the profiles, okay, you can immerse inside that. So, these are, we do not have a lot of it in our institute, but these are things people are using. So, this is called, now computation is third pillar of science along with theory and experiments. Presently there are people are saying there is a fourth pillar. What is the fourth pillar? So, data. So, machine learning. So, machine learning and computation are slightly different. So, in computation we typically assume that we are solving some equation or some model, but in data analytics or this machine learning we are not worried about what is the equation, we are worried about for this data I get this result. So, for some unknown data or for unknown input what will be the output. So, that is, people say there is the fourth pillar. Okay, I mean it is still evolving, let us see. So, machine learning I will not cover in this course, but there is one more. Well, the computation is typically, well, we will do classical computing, but the new game is quantum computing. Okay. And quantum computing is very different than classical computing. It has certain promise, definitely. There are some problems. Okay. So, I will try to give one lecture on quantum computing, either me or some guest lecture. So, we can explore what is the difference. Okay. So, there are lot of promises, but there are difficulties as well, and we will do it in one lecture in future. Okay, so I will just list out some major applications just to make you aware why it is important. So, flows, that is what I work on in my research. So, weather and climate forecast, okay, that is a very important application, especially now because weather is getting very erratic. So, flows around automobiles, aeroplanes, space vehicles, rockets, oil exploration. Lot of effort goes into oil exploration. We can't simply keep digging in on earth, and the digging is not 1 kilometer. The digging could be something like 10 kilometers drill. So, this is a important numerical simulation or numerical modeling. Physics of turbulence is theoretical, but this is what we do in our lab. So, flows in around stars, black hole, galaxies, planets. Okay. By the way, I will give you these slides, so you do not need to copy all of it. So, this I will make it available. Okay. Quantum turbulence is one more very hot topic right now. Okay. So, these are various sample of flow problems. Okay. Then materials and quantum systems. Okay. So, as I said, the materials for aeroplanes or vaccines, right. So, these are some things. So, quantum matter, now this is another big thing like transistors, no. So, and we are aware of silicon transistor, but people are trying some new material like spintronics, right. So, spin based on spins. So, lot of it is by computer simulations. Please keep in mind that many models, quantum models cannot be solved analytically. Electrons which are interacting strongly, they are very hard to solve analytically. People use quantum field theory, but not much success. Like high TC superconductor, there is still no theory, right. So, how many years? High TC is 40 years old now, 35 years, and we have no theory. So, all those systems we do lot of computing. Quantum Monte Carlo, these are methods which we will not do in this course, but I am just telling you. Density function theory, particle simulations, this we may do it in our course. Okay. So, these are various methods. So, nonlinear physics and health. Okay. Health is lot of emphasis on. So, epidemiology, well, this slide was prepared during COVID times. Now, for heart, lots of money goes in there, so simulate heart. And what should we do to keep heart healthy, how to basically without putting a probe inside, you should know whether how much of artery is blocked. Understanding brain is still not understood. Network, so network means electronic network means data network. Okay. So, this is a major problem. By the way, all our computers are connected by at least a billion other computers, right, billions of computers. So, there are models, in fact, there are very clever models to route the message. It is possible that data may be clogged, right. So, then everything will fail. So, these router models are very important models. Human body, okay, needless to say, is a lot of attention goes there. So, this earthquake is a very important problem. We still do not have very good prediction for earthquake or even rudimentary prediction of earthquake, but people are trying. Okay. So, complex physics, study dark matter and dark energy. Okay. So, I am giving you some astrophysics stuff. We do not understand them, but people are simulating. Okay. So, that dark matter, evolution of the universe, galaxy, stars, fusion research and tokamak. So, people say that this is possibly the most sought after energy source. Okay. Oil will go away after some time, coal is not good, solar we can't have at a very large scale, but fusion has not really worked so far. But and this huge amount of I mean, it is a complex problem, it is not easy problem. So, computer simulations, okay. Lattice QCD, right, this for modeling nucleons, accelerator simulations and data analysis. Okay. So, in fact, this colliders, particle colliders generate huge amount of data. So, when these particles collide, the high energy particles, they create a lot of other particles, and then they are all analyzed and to figure out where is eggs. And okay, so there are engineers here, so I do not want to be biased to physics. Okay, so let us look at some engineering problem. Buildings. Okay, now there are rare simulations for structures. Okay, in fact, for in this room, well, this very badly ventilated, but where should be the window? Okay, so where should we keep the fans? Now architects can show you this how your building will look like. Okay, so and we can look at the flow profiles inside the building. So people are doing this kind of work. Water network. So this one simple example I am giving you. So water in a city. Okay, so we can put in a computer. Chip design. This is a huge amount of money and effort. So computer chip. So simulations are done to make new chips. You know, this is a big crisis. Are you guys aware of this chip problem? Or so I'll tell you after this recording is over. Okay. So complex machines, rocket, engine, aeroplane, cars. Okay. So rocket inside the rocket. Okay. In rocket, I mean not only the launch, but India bought this engine for the fighter aircrafts, jet engine, right. So those engines are very hard to make, and it requires a lot of simulations and cleverness. Okay, so all of it, but the computer cannot think. Please don't misunderstand. The computer can think. It requires very good data knowledge experts of the field and good programmers. So it's always a combination of these two who can come up with a very good design. So it's not that computer will be told, okay, design engine and it will do it. Okay, that's why I am not so fond of machine learning. I don't believe that it can really design things. It's good for analysis of data, but not really is not as clever as what people think. Okay, transport. Okay, like it's a Google, Uber, and Ola. All these people are really interacting very live. So you've seen there are automatic cars. So Elon Musk is riding on an automatic car. Okay. Now automatic car is very, it's a complex machine. No? So it's getting data of the road, visualization, no pedestrian is walking. So it's a lot of data comes into it, and so whether this is a major problem, problem of interest commercially. Okay, machine learning, as I said, so it's now being applied everywhere, and it is a very promising application. Now coming to think of it, you can just think why Amazon is doing it. So we stock, a shopkeeper will stock certain things, right? For example, cereal, but this object has an expiry date, right? We can't keep it more than 2 years, it is wasted. So how much should the shopkeeper stock? Now understand, no? I mean, should I keep 50 bags, or should I keep 200 bags or 2000? So then machine learning can help. So you can look at last 2 years of sale data and then say, well, this is how we should do. Now there is a for solar guys who produce solar energy. Now solar energy is not available all the time, right? So they have to optimize how much panel they should invest on. So that depends on the requirement. If you put too many solar panels and there is no demand, boom, gone. And depends on season as well. So in winter, summer. So here data learning is very useful, because I can't make a model. I don't have a real model, but data analytics is very useful for such applications. Defense, right? I mean, huge amount of money goes in there. And economics, stock market, this is all computers, banking and forecasting stock market. People are working on it. So, in fact, I do not know, some mathematics student here. So, banks have to decide where to invest, put their money, they are huge money, or even rich people. So, they play with stocks. Okay. So, let us look at some example of complex calculation. We need to determine, given a problem, we need to determine how much resources I need. Okay, resource means how big a computer I want. Okay, you can't simply have a problem and put in your laptop and expect it to work. So, we will take a weather modeling or simulation of weather as a problem. Before that, let's look at estimate. So, I'm going to weather after this. So, typical desktop or laptop has 4 or 8 GB RAM. Now, some may have 16 GB RAM, but 8 is typical RAM size. GB everybody understand, no? You need all these words, okay? Gigabytes. So, to save a matrix of 1000 size, so 1000 by 1000, how much RAM do I need? Okay. So, what is the answer? Huh? Floating point, okay. Huh?
Depends on the size of each element, like float, that one.
I said float, I mean double, let's say double. Double how much?
8 bytes.
Okay, and we have 1000 cube data, not 1000 cube, 1000 squared. So, we have, what is our matrix size? How many elements? Million, right? 10 cube into 10 cube, million. Okay, and so each number float a double takes 8 bytes. So, 8 times 10 power 6, which is 8 megabytes. Okay, and for float it is 4 megabytes. Okay, this is what we need. Now, if your matrix size is, this will fit in your laptop, but imagine your matrix size is 10 power 5 into 10 power 5, then what happens? So, it is 10 power 9, 10 power 10. So, it is already, so multiply this by 8. So, it is going to be 80 gigabytes, right. So, 80 gigabytes cannot fit in your computer. Okay. So, you can handle 10 cube, but not 10 power 5. Okay, the other example is if I have 4096 cube grid. So, it is a 3D grid. Okay, in this room I make a 4096 data points in each direction. Then the memory requirement you can see is, so this is how we should estimate. So, 4 cube is going to be 4 into 4 is 64. So, this is 4096 cube will be not exactly 64 10 power 9, because look, 1024 is 1 kilobyte. It is not equal to 1000, but approximately 1000. So, we write is 10 cube. So, we write this is 8 is for double, 8 64 and 10 power 9, and is going to be 256 times 10 power 9, which is 1/4 terabytes. Okay. So, it requires 1/4 terabyte space. Okay. So, these problems are done in research, not quite often, but you need a bigger machine than a laptop. You can easily see, right. Okay, so let us look at space. So, there are two complexities, space complexity and time complexity. Space complexity is RAM and hard disk as well, but we should fit all the data in RAM. If you put in hard disk and keep bringing back and forth, that is not practical nowadays. Okay. So, we want to do this weather simulation. So, make a grid of Earth atmosphere is spherical object. So, we make a 3D mesh. So, you can think of a spherical spheres, and I am going to make 1000 well, I think I have 1000 spheres stacked. For each sphere I make a 3 kilometer by 3 kilometer grid. So, I hope you understand. So, I make a mesh. So, this grid, these points are separated by 3 kilometer in x and y direction or azimuthal and longitudinal direction. Of course, it is not a uniform mesh like a cube, okay, but there are ways to do it. So, we will not worry about it right now, but we make a mesh like that. So, imagine the maximum distance is 3 kilometer by 3 kilometer. So, Earth radius is so 2 pi times 6000, right, that is our circumference. So, you divide by 3, so that I believe is something like 12,000. Okay. So, 12,000 by 12,000 horizontal mesh 2D. Now, in third direction as I said, I make 1000 spheres. So, the data point you can work it out 12,000 into 12,000 into 1000, that is like 144 times 10 power 9. Okay. So, each of them is 8 bytes for double and there are 7 variables. So, 3 components: velocity, pressure, temperature, humidity. Okay. So, that makes there and I believe one more. So, there are 7 variables, okay, in Earth atmosphere simulations, minimum 7. So, that requires 8 terabytes for a single copy. Why do I say single copy? So, you may know Rangakutta method, no? So, you make future, present and intermediate for RK2. So, you will have to make at least 3 copies, right. You can't, so 8 terabytes per copy. So, we need huge RAM. Okay. Now, time complexity. So, let us take a 1 minute resolution. What does it mean? So, I am going to time advance this equation, Navier-Stokes equation and temperature equation every minute for minute of our physical time. Okay. I want to do 3-day forecast. So, I am going to start from initial condition right now and every minute I will time step and reach 3 days. So, what should be the number of time steps? So, these 3 days, 24 hours and 60 per hour. So, that is 4320 time steps. Whether 1 minute is too big, but we can't do better. You see how much time is going to take. Okay. Now, grid points, as I said in the previous slide, we keep the same grid, which is a very fine grid, but this 144 times 10 power 9 grid points. Now, we assume that each, so I need to compute all these variables at each grid point. Please recall your earlier study of finite difference method, no? Every grid point I want to update the variable, and this update, imagine that it requires 10,000 floating point operations, multiply, divide, multiply with 3 and so on, right. So, pi is there. So, 10,000 may be slightly overestimate, but I am just estimating 10,000 floating point, but there are 7 variables. Huh? So, I have 7 differential equations. So, how many floating point operations are required for each time step? So, I just multiply the number of grid points, number of time steps required, 4320 time steps required, and this is 10 power 4. So, I need this many floating point operations overall for 3-day forecast. So, 6.2 times 10 power 18, okay, this is exa, 10 power 18 is called exa. Computer, in our computer center we have petaflop machine, okay. So, petaflop is 10 power 15 operations per second, okay, 100% efficiency, okay, which is never obtained, but 100% efficiency. How long will it take? So, this divide by 10 power 5. So, it can do, our machine can do 10 power 15 operations per second in ideal time, ideal environment, when there is no problem, no loss of data, time loss due to data communication. Okay. So, that will be this 6.2 10 power 18 divided by 10 power 5, which is 6200 seconds, which is 100 minutes. So, it is going to take 1.5 hours or more if it is 100% efficient on that machine, if you have all the machine. You will never get 100% efficiency, for we get around 2 or 3% efficiency, okay? Because well, we will see that when we do the course, where are the losses, but let us do the best possible case with 10% efficiency. It will still take 1000 minutes, which is just multiplied by 10. So, something like 15 hours. Okay. So, this is the time complexity. Okay. Now, that is why we need bigger and bigger machines and better machines. Okay. And that is what this course is about. So, what are the steps being taken? So, one thing is the hardware is getting better and better over time. So, I am just going to show you the hardware, how things are getting better. So, 1972, one processor 1972, Intel 4004 had 2300 transistors, okay, and it could do only 60,000 operations per second, okay, 60,000. Now, your mobile is doing much better than this, huh? But 2023, this is the best processor right now available, okay. You can just check EPIC 9754, this by AMD, is called Genoma series, okay. It has 82 billion transistors, okay. Now, see the ratio 2300 and 82 billion, and it can perform, I am not too sure about this, I need to check, 4 teraflops, 10 power 12 is tera, okay, that many operations per second, okay. So, compare 60 kilo with, which is 60,000 with 4 times 10 to the 12, okay. So, we have gone a long way in terms of power of the computers. Now, it turns out this is not the final game. The big news right now for computing is GPU, okay. So, GPUs can do much better than this, much better than this, okay. They are cheaper and faster. So, we'll in fact, this course I will focus more on GPUs. Presently, most of the supercomputers in top 10 are GPU based. They are not using this CPU, which is very fast, but CPU is not, is 100 times slower than GPUs, okay. So, I will give an example which, so we have a GPU which is NVIDIA's GPU A100, okay. So, this GPU compared to single EPIC processor, not this processor, we have ROM processor, one generation earlier. So, the A100 performs 3000 times faster compared to ROM processor. So, single core of ROM processor. Now, these words you may not be familiar with. ROM has 64 cores. You heard this, no? 8 core machine, 4 core machine. So, this guy has, I did not write it here, it has 128 cores, okay. Your laptop probably have quad core or octa core now, but this processor has 128 cores. Now, GPU has 6000 cores. These guys are, the GPU is much faster than the single core. So, even if I could get all the 128 cores to perform, they will not be 100 times faster, but this guy A100 is beating this processor 30 times, okay. So, that is the power of the GPUs, and that is why people have moved to GPUs, okay. And so, we will cover quite a bit of architecture in this course. It is not simply that you know how to program, because programming paradigms change with hardware, right. Your C program will not run on a GPU. So, you may be a very good C programmer, but if you can't program GPUs, no good, okay. So, programming paradigm is changing very rapidly, okay. So, just to give an example, I wrote a code which was in C++, which was very good code, but we started doing this in 2006 and so on, and that was nice code, it worked very well. but when the GPU came, this code is not very attractive anymore, because this code, my code does not run on GPUs. C++ porting on a GPU is not very well, it's too much labor. One of my students is very good in this, so you have to write in a new language called CUDA. Okay. So this code converted into CUDA is a quite a bit of a challenge. It turns out then we move to Python. So Python code, which is smaller in size, and it can be ported to GPU very easily. Okay. But the performance is not 5000, 3000 times, it is around 500 times, or possibly we made 1000 times. So CUDA is definitely faster, but Python is easier, and easier for the programmer as well as for the user. The problem is, with the due respect, there are people who are stuck with Fortran, no? Say, well, Fortran is the best language, or I don't know anything other than Fortran, I don't need anything other than Fortran. But it turns out a lot of things which can be done in C or C++ cannot be done in Fortran. Okay, the class structure is very useful in C++, can't be done in Fortran. And then, like, GPUs are basically in C++ or C. So Fortran support is basically going to go away very soon. Okay. So these languages, choice of language change. So people who are very good, they made a lot of name with Fortran, big codes. They had to search for new ideas, or well, not they will search, they will change. Okay. So, and also visualization, it is not simply C++ code, there are packages. People who write the software, they have to know much more than just the language. Okay. So that's the complexity. So that's why this field is changing so rapidly that it is very interesting, but also very tiring. You have to keep learning new things. So course, just give a broad outline. Hardware, we will cover it. So I think, as I said, without knowing the hardware, you cannot optimize your code, or you cannot not even optimize, you don't know what to choose. Okay. So I will cover processor, memory, interconnect, shared memory and distributed memory, software aspects, simple tricks to speed up. Okay. I will show you that doing one simple stuff, we can speed up the code by factor 10. Okay. This vectorization, you people have heard of this vectorization? So for Python, if I want to multiply two arrays, okay, so you may simply go for any language, no, for I equal to 0 to number of variables, Ci equal to Ai times Bi. That is what you would go to write a code, but that is not a good code. Okay, you should not do this. In fact, the thing you should do is write C is an array, you define array, C equal to A star B. It's simpler to write, but this is depending on the grid size, it will be at least 15 times faster than the above one, and this called because of vectorization. So processor can do many things at the same time. So when I write like this, C is A star B, then processor can take lot of data in one clock cycle, it can do this in one shot. But if you write like A star B, well, actually programs are not clever, Python will convert into this, but if you put if inside, okay, then Python won't know. So if I greater than 10, do this, else do that, that's it, your vectorization is broken. You understand what I am saying? Because the guy won't know which data I should do in one shot, which data I should not do in one shot. So it won't work. Okay. So if statement within for loop is to be not used. Okay. Now this requires certain planning, and your code will be definitely 10 times faster if you follow some of this practice. So we will do MPI, which is message passing for distributed computing. So, now parallel computer, what is a parallel computer? Parallel computer is that we have lots of processors working together. Okay. So, we will also discuss why we are doing that way, but this is the presently what is done, lot of processors working together, and we need them to communicate, and that is by MPI, message passing interface. Multiprocessing, multi-threading is possibly not looking very familiar words to you, but we'll do that. OpenMP and this GPU programming. I will spend quite a bit of time on this. Okay, it turns out this is much simpler than doing MPI and so on. Well, I won't say much simpler, but once you learn it, then you can do it quite well. And we'll see how to work with large data. I'll try to take one or two lectures, one lecture on this and this, and also we'll probably take one on quantum computers. Okay. There are lot of books, but since the field is rapidly advancing or rapidly evolving, these books are basically become out of date very quickly. So, the way to go is they look at websites. For example, this website is for CUDA Python. So, how to write Python code for GPUs, okay, and so that is more common. This book will use it for MPI and so on. This is a very nice book. Okay, these are some details on hardware. I have collected material from various sources, and that is what I will present. Okay, so but finding a one book is definitely not possible, but even these books which are good, but they are basically some of them are out of date. So, computer architecture, there is one famous book by Patterson. Okay, Patterson and there is a co-author. So, I have taken a lot of material from Patterson's book. Okay, so I think we will end here.